So in a previous video, I gave you two questions to use dimensional analysis with. If you haven't seen that video yet, or if you haven't worked through these yet, you can stop this video, you can go back and look at those other questions first. You can look at the video that has the questions first before we go over them so you can practice them on your own. What we're going to do is we're just going to work through these step by step. And so here's the question. We want to make an equation using dimensional analysis, then we want to solve the problem. The price of a box of cereal is $2.98, and the price per ounce of the cereal is $0.134. What is the weight of the cereal? All right, so the first thing I want to do is I just want to write some things down that I know. I know that my cost is $2.98. I know that my price per ounce is this. And I'm writing it this way. Over here I have the price per ounce, and in parentheses I say it's dollars over ounce. I could say this as price per 1 ounce. There is a understood 1 underneath here. So for every 1 ounce, this is the price. And what I want to do is I want to somehow combine all this information to give me, and what I want in the end is how many ounces of something. And so what I'm going to do is I'm really just going to want to play around with all these numbers until I can cancel out units so that I get ounces by themselves. And so the first thing I can do, and if you say you want to combine these, first off, I know I can't add them because my one number over here, this is in dollars, and this is in dollars per ounce. Those are not the same dimension. I can't add them together. So I know that I have to either multiply or divide here. And so I'm just going to start with the first thing that comes to my head and say, hey, let's multiply these. I'm not going to put in any numbers right now. I'm just going to look at the dimensions because this is dimensional analysis. Price, that's this first one here, $2.98. And I'm going to multiply that by my price per ounce. It's not a 2, that's an ounce. Now, one of these looks like a fraction, one of them doesn't. We know that everything can be written as a fraction if I just put it over 1. And so I'm going to put a 1 over my dollar sign so that it makes it a little bit easier to keep track of what's happening. So here I have a price times a price on the top. And then on the bottom I have 1 times ounce, which equals an ounce. So my question here is, if I were to plug in my numbers here, do I get ounces? No, I don't. Yes, there is an ounce here. It's in the bottom of my fraction, but I also have this money squared at the top, this price squared at the top. So that's not going to help me at all. All right, so what happens if I say, well, that didn't work? What if I were to flip one of these upside down? And so let's take a price per ounce and multiply it by the inverse, or the reciprocal of my $2.98. So I go 1 over my price. This is the same thing as dividing. I could say I'm taking my price per ounce and dividing by my $2.98. I like multiplying by reciprocals. That's just what I prefer here. Now, if I were to do this, some things start to cancel out, and so you can get a little bit excited here and say, this is interesting. I have a dollar on the top here, and I have a dollar on the bottom there. Since one's on the top and one's on the bottom, they're going to cancel out. Well, now I'm only left with ounce, and that's what I want. So now I multiply across the top. I have a 1 left on the top. I multiply it on the bottom, and I have an ounce left on the bottom. But I have to be careful here, because what I want in my answer is I want the number of ounces. I don't want 1 over ounces. And so I'm close. I did something right, but I haven't finished all the way yet. And so I have to get my ounces back to the top. Now I noticed that when $1 sign was on the top and $1 sign is on the bottom, my dollars cancel out and I'm left with my weight. But what would happen if I flipped the other thing? So in this case, I'm going to go with my ounce on the top, my money on the bottom, and I'm going to multiply that by my money on the top. Well, my money cancels out, and I'm left with ounces. So now I have an equation that works. I can now solve this if I plug in my numbers. So let's go ahead and do that. For this first piece here, it was ounce over price. I have price over ounce. So simply all I'm going to do is I'm going to invert this. I'm going to put my ounces on the top, 1 ounce over $0.134, and I'm going to multiply that by my money. I'm not going to invert it or anything. It strictly just says keep the money the way that it is, and so I'm going to multiply this by $2.98. My dollar signs cancel, and when I do the math on this, I get 22.074 blah 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 ounces, and it goes on for a little while. So what I could do at this point is I want to kind of check my work, and I can check my work with my units, and my dimensions work, so I can feel confident that I at least did something well. I had a good model to put this into. Then I would need to say, well, did I plug in my numbers correctly? There was a decimal here. Did I remember to put that in? And so then I look back, and we kind of talked about estimation earlier in the quarter and how it can be important here. I can look back and say, you know, I bought cereal before, and it's, I don't know, $3 or $4 a box, and 13 cents an ounce seems reasonable. How heavy are most boxes of cereal? And I could say, oh, let's say about a pound or so, and a pound is 16 ounces. And so then I could look back and say, does this seem reasonable? Yeah, I mean, it's not exactly 16 ounces, but it's around there. It's not like the box of cereal weighs half an ounce, or it's not like it weighs like 300 pounds or anything. And so it seems reasonable. So that gives me one more little bit of confidence that what I did was correct. And the last thing that I could do is I could use my significant figures. And we talked about that a little bit in some other videos and in class as well. What I have here is, since everything's being multiplied and divided, I'm going to look at what I have in my numbers. Now, my starting number here has 3 significant figures. And this number here has 3 significant figures as well. You might say, well, there's a 1 on the bottom there. We're considering that a perfect relationship, that there is exactly $0.134 per ounce. And so this one we would also say has 3 significant figures, which means my answer can only have 3 significant figures. 1, 2, 3. And since this fourth number here is 5 or bigger, I'm going to round up and say 22.1 ounces. I always like to box my answers, make sure that I show exactly what I have, because there's a lot of work here. I want to make sure that I get credit for that final piece that I got. All right, so the next one was using F equals ma, the force equation, and breaking it down into its fundamental dimensions. Now, we've done most of this before. We'll work through it quickly here, and if you have questions, we can talk about it in class, or you can go back to some of those other videos maybe where we talked about it a little bit more in depth. But what I have is I'm going to rewrite my equation. And what I want to do here is I want to figure out what force is made up of, but since I have an equal sign here, that means whatever is on the left is the same thing that's on the right. The stuff on the right, it's already in pieces. Ma is a force, but it's not, it doesn't look like a force. It doesn't just have an F. It tells me that a force is made up of a mass times an acceleration. So what I'm going to do here is I'm not going to worry about this side with my force. I'm going to start breaking apart this side. And I'm going to start off by just looking at my very first variable, which is an m. That's mass. And lucky for me, mass is a fundamental unit. And so I can say that's great. Force equals a mass, and I'm going to capitalize my m this time, times whatever acceleration is. So you can be like, wow, I'm halfway done. Sometimes there are parts of the problem that go pretty quickly. The mass side goes pretty quick here. Now we're going to break apart acceleration. Well, an acceleration is a velocity over time, or a change in velocity over time. And a velocity is a length, L over T, a length over time. And so I could substitute that in, and I could say, well, if acceleration is a velocity over time, that means an acceleration is a length over time over time. Well, I know what a length is. I know what a time is. And if I look over here, I have a length and I have a time. And so at this point, I could say my acceleration equals a length over time over time. And there's a couple ways that we can simplify this. I talked about this in the more dimensional analysis video. I like to look at this as fractions and break this apart into my acceleration equals a length over time. And instead of dividing by time, I could do the same thing as dividing, which is multiplying by the reciprocal. And this really helps me see that my length's on the top and both my times are on the bottom. And so I can say that my acceleration equals a length over time squared. So now I'm going to go up and put that into here. Force, keeps getting me out of my drawing. Force equals m times a length over a time squared. And I can simplify this. I can make it look a little bit neater. Maybe not with my handwriting, but at least with my math here, and say that force equals a mass times an acceleration all over time squared. So now anytime in the past, currently, or in the future, there is a force somewhere in the world or in the universe or in a problem that you're working on in engineering or physics or chemistry, what we're really saying is that there's a mass times a length divided by a time squared involved.